Atkinson, which perhaps you can start sharing your screen.
Oh.
And Craig Atkinson received his PhD in computer science from the University of Otago in Dunedin, New Zealand. I'm not sure if I'm pronouncing it well, in 2020. And his research interests include deep reinforcement learning and continual learning. He now works on machine learning projects at Fonterra dairy company, and still basically his PhD was on achieving continual learning on deep neural networks through Pseudo-Rehearsal, which is the title of the talk of today, which is of our interest. So please, the floor is yours.
Cool, thank you. You can see my screen, right?
Yes.
Awesome, cool. All right. Hi everyone, so I'm Craig. Thanks very much for tuning in. Today I want to talk to you about how pseudo-rehearsal can be used for achieving continual learning. So we had a good summary just before, but essentially continual learning, just to cover our bases, that's the ability for a neural network or a model to persistently learn over time, and that is integrate new knowledge with previously learnt knowledge. One of the big problems that neural networks find here is catastrophic forgetting, and that is the neural network's tendency to forget your previous knowledge when it learns something new. So if we take a sequential learning task, for example, if a neural network's already learned task 1 and it begins to learn task 2, catastrophic forgetting will often occur, and this is where the accuracy of task 1 very quickly drops off to often levels like the task had never even been seen by the network before. And it's that dramatic drop that is called catastrophic forgetting. And that's mainly going to be what my talk is going to be about, overcoming for continual learning. So one of the easiest solutions, I guess you could say, or simplest solutions for overcoming this problem is rehearsal. And that is where you learn data from your new task while you're rehearsing data from past tasks. The problem here, or one of the limitations here, is that that requires you to store data from all of your previously learned tasks, and that, as lifelong learning goes on, would end up being a lot of data. And so that is where pseudo-rehearsal comes in as an alternative solution. In your simple pseudo-rehearsal, you learn the data from the new task while rehearsing data from these pseudo-items. The pseudo-items there, the inputs of the pseudo-items are just randomly generated numbers, often with a random number generator. And those inputs are then put through your previous neural network to attain the desired or target outputs. And therefore, the pseudo-items that you have that you learn alongside your new task hopefully captures the function of what the neural network had previously learned, and therefore prevents forgetting. There are still some limitations to this though. Primarily when you start moving into larger input spaces or more complicated input spaces, simple random number generators don't do enough. For example, for an image, if you use a simple random number generator, you're just going to generate images that look like static, and those images are not going to be very representative of previously learned tasks, most likely. For example, if your past task was teaching the network to classify horses, static images are not going to contain many useful features to remind the neural network to remind the neural network what a horse looks like. And again, this is where extensions have been made, and so methods like deep generative replay and pseudo-recursal has paired these pseudo-rehearsal algorithms with generative networks, so that now the generative network can be used to generate more useful pseudo-items. And so that generative network there is just trained sequentially alongside your main network, so that when a new task is being learnt, the generative network can be used to generate examples from previous tasks, and they become your pseudo items. And they can be and the inputs that are generated can be fed through your neural network to get the target outputs. And those pseudo items can then be learned with your new task and prevent retention very well. For the remainder of the talk, I kind of want to talk to a bit more about my research in this domain. So this is the model here that I'll be talking about is the reinforcement pseudo-rehearsal model, or REPA for short. And this was work that I did with my supervisors for my PhD, Brendan McCain, Lex Szymanski, and Anthony Robbins. So the REPA model, the example I'm going to show you, the REPA model will sequentially learn 3 tasks. Those tasks are reinforcement learning tasks, the Atari 2600 video games, and they're going to learn the games Roadrunner, Boxing, and James Bond in that order. First, I'm going to show you what the model looks like and how it's trained, and then show you some results. So the model comprises of 3 components. You have your short-term memory, your long-term memory, and then a copy of your previous long-term memory. The goal of the short-term memory is to interact with the environment and learn the new task in isolation. The goal of the long-term network is our continual learning model, essentially. So its job is to integrate that new knowledge in with what it already knows. And the previous long-term network or model component, I guess, that part is just a copy of our long-term system before it begins learning the new task. And that component is just used for generating our pseudo items for retention. So I'm going to go over the 3 stages of training this model. And we're going to assume that the model has already been taught the tasks Roadrunner and Boxing, and just has to learn the final task, James Bond. So in the first stage of training, the short-term reinforcement learning agent learns James Bond by interacting with the environment, and it does so through reinforcement learning. Once the model has learned how to play that game in isolation, then that knowledge can be transferred to the long-term agent. And this is done by taking the input examples or the states from the game James Bond, passing them through your short-term reinforcement learning agent to attain the desired outputs, and then teaching that to the long-term agent. However, we need to prevent forgetting here, and this is where pseudo-rehearsal comes in. And therefore, we use our previous long-term generator to generate examples from the past tasks, that is the Roadrunner and Boxing. Those example states are then put through the previous long-term agent, because that agent knows how to play those games, and therefore it gives it the desired outputs for each of those input states. And then together, that is all fed into that long-term agent. So your long-term agent is now learning data from your current task and generated data from your previous tasks, and therefore it will learn to perform well on all of the tasks. The final stage of training is where we train our generator in the long-term memory. This is done by taking the input states from the James Bond while the short-term reinforcement learning agent is interacting with the environment, and learning those states again alongside our pseudo items, which are just produced by the long-term generator. This results in our long-term generator being able to generate input states from all 3 of the tasks. And this is important because, say, a 3rd task comes along, well, now we have a generator which we can copy to over here in the previous long-term network. And that generator can then be used to generate pseudo items from all 3 of the previously learned tasks, so that now that 4th task can be learned. So hopefully I can show you guys some videos of what the agent looks like after it's done pseudo-rehearsal to learn the tasks. So, sorry, that always happens. Where's the mouse gone? Here we go, cool. So here we have, so this is after Reaper has learned all 3 tasks. So it learns them in order from left to right. We have Roadrunner here on the left. The Roadrunner agent is the one in orange there. It is it's learned to run away from the coyote and collect the points on the ground, as well as moving or dodging the hazards and moving so that the coyote then runs into those hazards to slow it down. So this task was the first task that had been learnt, and then later on, these 2 tasks here were learnt. And as you can see, the Reaper model has successfully prevented catastrophic forgetting, as the model's performing very well here. The middle game here is boxing, and the agent is the white character in this game. And as you can see, hopefully by the scores here, the white agent is performing very well. And essentially, in this game, you score points by smacking the other character in the head. And the agent here, the Reaper agent here, has learned to essentially juggle left and right, like you see there, smacking the other character in the head for more points. And again, this shows that the network's done very well learning these tasks and then retaining it. Finally, over here, we have James Bond. James Bond's the most recently learned task, and therefore catastrophic forgetting can't really or shouldn't really occur. And as you can see, hopefully, the James Bond card there is performing very well. It's shooting the light bulb looking things for attaining points, and it's generally, I say that as it kills itself, but it's generally avoiding the obstacles or the hazards in the game. I can quickly show you what it looks like when you don't do, or you make no effort to retain your past tasks. So this is if you do not do any pseudo-rehearsal or any of the other methods for preventing catastrophic forgetting. So as you can see, hopefully, now the first 2 games that were learned are performing much worse. So the Roadrunner here is getting caught by the coyote very quickly, and the game is a lot more even in the boxing scenario. But because James Bond is the most recently learnt task, that task is not catastrophically forgotten, and the James Bond is managing to collect points very well in this game. So just a couple of slides to wrap up. So this slide here shows how good quality the pseudo items are that are produced by the generative network after it's learned all 3 of the tasks. So those pseudo items are here on the right. And as you can see, they do a very good job of mimicking what real items or inputs look like on the left there. Besides a couple of notable points, mainly there's some fuzziness around moving components in those images. But in general, it does a pretty good job or the generator does a pretty good job after sequentially learning to produce useful input states of the previous tasks. And this is backed up by the performance because we find that the Reaper using pseudo-rehearsal performs just as well with those generated images as it does if it was to learn or retain using real inputs from the past tasks. And a few points on what are the limiting factors of pseudo-rehearsal. So the capabilities of pseudo-rehearsal are still limited by the power of...
Sorry.
Yeah, perfect. Just wrapping up, so all good. The capabilities of pseudo-rehearsal are still limited by the power of our generative network, and therefore our generative network, as our generative network becomes more powerful, so will pseudo-rehearsal. So hopefully in the future, generative network will be able to represent more complex or generate more complex input spaces as well as multiple domains. And that will have a positive effect on pseudo-rehearsal itself. And finally, there's also a chance to specialize generative networks for pseudo-rehearsal, and that is by training them so that there's more emphasis on them generating features which are useful for retention over more redundant features that aren't useful for retention. And yeah, I'm very interested to see where pseudo-rehearsal goes. and hopefully it's becoming more and more useful in the future. Yeah, that's all,
Okay.
folks.